Picture this. You're walking through a forest in medieval England and you stumble across something that looks like organized chaos. Dozens of people are hauling massive wooden beams, shouting instructions over the sound of axes and saws, and somehow turning a pile of freshly cut oak into what will become someone's home for the next 3 centuries. No cranes, no power tools, no Home Depot run when they realize they're short on nails. Just human hands, ancient techniques, and wood that's still got bark beetles complaining about their sudden relocation. This isn't just construction. This is timber framing, and it's about to blow your mind with how clever our ancestors were when they had nothing but sharp tools and centuries of passed down knowledge. We're talking about a building method so effective that houses built this way are still standing today, probably in better shape than that apartment complex they threw up last year with modern materials. But here's the thing that'll really get you. These weren't just random people with axes having a good time. Every single cut, every joint, every piece of wood was planned with mathematical precision that would make modern engineers jealous. They were creating structures that could flex with earthquakes, survive centuries of weather, and do it all without a single nail holding the main frame together. 0. Not one nail in the entire skeleton of the house. The process starts in the forest. And trust me, these medieval carpenters weren't just wandering around pointing at random trees like they're picking apples. Finding the right oak for a timber frame house was like a master chef selecting ingredients for a feast that had to last 300 years. They needed trees that were straight as arrows, free from knots, and seasoned by nature in ways that would make modern lumber yards weep with envy. The first rule of oak selection was simple, but brutal. No shortcuts. A twisted tree might look fine from a distance, but try building a house frame with warped timber, and you'll end up with walls that look like they were designed by someone who'd had too much ale. Medieval carpenters could spot problem wood from 50 paces. They'd run their hands along the bark, checking for telltale bumps and irregularities that meant trouble lurking inside. Here's where it gets fascinating. These guys understood wood grain better than most people today understand their smartphones. They knew that oak cut in winter would be denser and stronger because the sap was down. They knew which part of the tree would make the best posts versus the best beams. Some master carpenters could look at a standing oak and mentally map out exactly which timbers they'd get from each section. Talk about planning ahead. The felling process itself was nothing like the chainsaws and machinery we see today. Picture a team of men with axes that weighed more than a modern sledgehammer, taking turns to chip away at a tree trunk that might be 3 feet across. This wasn't random chopping either. They'd score the bark in precise patterns, creating weakness points that would help the tree fall exactly where they wanted it. Missing your target could mean crushing months of work or taking out your neighbor's prize pig. Once the tree was down, the real artistry began. Riving was the process of splitting the oak along its natural grain lines, and it required an almost supernatural understanding of how wood wanted to break. Using wedges and a tool called a froe, they'd split massive logs into manageable sections. The key was reading the wood's personality. Some oak split clean as a whistle. Other pieces fought back like they had a personal grudge against becoming house parts. The sound of riving oak was apparently something special. Old accounts describe it as a sharp crack, followed by a long, satisfying split that could be heard across half the village. Some master carpenters claimed they could tell the quality of the wood just by listening to how it split. A clean, resonant crack meant good timber. A dull thud, followed by splintering, meant someone was about to have a very bad day. But splitting the wood was just the beginning of the transformation. Now came the real test of skill. Hewing. This is where a rough log became a precisely shaped beam through nothing but human muscle and a tool called an adze. Imagine trying to shave a tree trunk smooth using what's basically a sideways axe, and you need to get it perfectly square and straight, or your entire house frame won't fit together. The master hewers were artists in their own right. They'd chalk lines on the log to mark where they needed to cut. then systematically remove wood with strokes that had to be both powerful and precise. Too aggressive, and you'd gouge too deep, ruining the timber. Too gentle, and you'd be there until Christmas, assuming Christmas was still several months away. The rhythm of hewing became second nature. Swing, cut, step, swing, cut, step. Hour after hour until a rough log became a beam smooth enough that you could run your hand along it without getting splinters. The really impressive part was the accuracy these guys achieved. We're talking about beams that were square within fractions of an inch, all done by eye and feel. No laser levels, no measuring devices beyond a piece of string, and maybe a crude square made from wood scraps. Yet these beams fit together so perfectly that the joints would stay tight for centuries. Different parts of the house required different techniques. The main posts, those vertical pillars that would carry the weight of the entire structure, needed to be hewn perfectly straight and square on all four sides. The plates, the horizontal beams that would sit on top of the posts, required different treatment. They needed grooves cut into their tops where the rafters would sit, and these grooves had to be spaced with mathematical precision, or the roof would look like it was designed by someone having a bad day with geometry. The tie beams were perhaps the trickiest of all. These massive horizontal pieces would span the entire width of the house, and they had to be strong enough to keep the walls from spreading apart under the weight of the roof. Getting the curves just right so they'd bear the load properly was an art form that took decades to master. Make sure to hit that subscribe button if you're enjoying this deep dive into medieval construction techniques. I'd love to hear in the comments which part of this timber framing process surprises you the most. Is it the precision they achieved without modern tools? Or maybe the fact that they could plan an entire house frame in their heads? And definitely give this video a like if you're amazed by what people could build with nothing but axes and centuries of know-how. The workshop where all this shaping happened was usually set up right in the forest where the trees were felled. Moving these massive timbers was no joke, so smart carpenters did as much work as possible before they had to haul everything to the building site. The setup looked like something between a lumberyard and a medieval art studio. Wood shavings piled knee-deep, the constant sound of metal on wood, and the sweet smell of fresh-cut oak that apparently made the whole operation smell better than most places people lived. But the most crucial part of the entire process was something that would drive modern contractors absolutely crazy. Seasoning. These freshly hewn timbers couldn't be used immediately. They had to sit and dry, sometimes for years, before they were ready for construction. Green oak, as they called freshly cut timber, was too unstable. It would shrink and warp as it dried, potentially destroying the careful joints that held the whole frame together. The seasoning process was both art and science. Timbers were stacked with spaces between them, so air could circulate, but not so much space that they dry too quickly and crack. They were covered to protect from rain, but left open to the breeze. Some master carpenters claimed they could tell when a timber was properly seasoned just by the sound it made when you tapped it with a hammer. Others relied on the wood's color changes or even its smell. Here's what made the whole seasoning process even more impressive. The carpenters had to plan years in advance. If you wanted to build a house next spring, you needed to start selecting and preparing timber the previous fall, maybe even earlier for the largest pieces. This wasn't just construction, it was long-term strategic planning on a level that would impress modern project managers. The economics of all this preparation were staggering. A typical timber frame house required between 40 and 60 major timbers, each one representing weeks of skilled labor to select, fell, rive, and hew. The cost of the wood preparation alone could equal what a craftsman made in an entire year. But here's the thing that made it all worthwhile. These houses would outlast the people who built them, their children, and their children's children. The quality control during this preparation phase was ruthless. Any timber that showed signs of defects during seasoning was rejected without mercy. A single weak beam could compromise the entire structure, so carpenters learned to be absolutely brutal in their standards. Better to start over with a new timber than risk having your reputation destroyed when the house collapsed during the first big storm. But once the seasoning was complete and the timbers had passed inspection, something magical happened. All those individual pieces of shaped oak were about to become the skeleton of a home through a process that combined engineering precision with community celebration. The layout phase was where years of preparation met the moment of truth, and where medieval carpenters proved they could plan an entire building using nothing but geometry, string, and an almost supernatural understanding of how wood wanted to fit together. The layout process was where medieval carpentry turned into something that looked more like a giant puzzle competition than construction work. Picture the village green transformed into an outdoor geometry classroom, except instead of chalk and blackboards, they're working with timber beams that weigh more than a small horse. The master carpenter would arrive with his layout tools, a collection of wooden squares, plumb bobs, and measuring rods that looked deceptively simple, but were precision instruments passed down through generations. First came the selection of the layout site. This wasn't random. They needed a flat area large enough to lay out entire wall sections called bents at full size. The ground had to be level enough that a rolling timber wouldn't gain momentum and crush someone's foot. Most importantly, it had to be close enough to the actual building site that they wouldn't need to organize a small army just to move the assembled pieces later. The layout itself was mathematical wizardry that would make modern architects weep with envy. Using nothing but rope, wooden pegs, and centuries of accumulated knowledge, the master carpenter would mark out the exact dimensions of each wall section on the ground. Every post location, every joint, every angle was planned to the inch. They call it full-size layout because that's exactly what it was, drawing the entire house frame at actual size on the ground using the earth as their drafting table. Here's where it gets mind-blowing. These guys were essentially creating blueprints, but instead of paper, they were using the ground itself. They'd drive wooden pegs to mark where each timber would go, then use ropes to connect the pegs and create the outline of each wall section. The precision required was staggering. A mistake of even half an inch in the layout could mean joints that wouldn't fit together when it came time for assembly. The scribing process was where the real artistry showed up. Each joint location was marked using a tool called a scribe, basically a compass with very sharp points. The master carpenter would hold the scribe against the timber and mark exactly where mortises needed to be cut or where tenons needed to be shaped. These marks weren't suggestions, they were precise instructions that had to be followed exactly, or the entire frame wouldn't fit together. But here's what made the whole process even more impressive. They weren't just marking one timber at a time, they were marking entire wall sections simultaneously, ensuring that every piece would fit with every other piece when the time came for assembly. Imagine trying to solve a three-dimensional puzzle where every piece has to be custom carved to fit perfectly with multiple other pieces, and you're doing all the planning while the pieces are lying flat on the ground. The joint cutting phase was where years of apprenticeship either paid off or got you laughed out of the carpentry guild. Mortise and tenon joints were the backbone of timber framing, basically creating a male piece that fits into a corresponding female socket. The precision required was absolutely brutal. Too loose and the joint would be weak. Too tight and you'd split the timber trying to force it together during assembly. The mortise was the square hole, usually cut into the vertical posts. Creating these required a combination of drilling and chiseling that tested every aspect of a carpenter's skill. They'd start by boring a series of holes with an auger, then clean out the remaining wood with chisels. The walls of the mortise had to be perfectly straight and square, and the depth had to be exact. One sloppy mortise could weaken the entire structure. The tenon was the projecting piece that would fit into the mortise, usually cut on the ends of horizontal beams. Shaping a tenon required incredible precision with hand tools. Too thick and it wouldn't fit. Too thin and it would be weak. The shoulders of the tenon, the parts that would bear against the face of the post, had to be perfectly square and smooth. Any gaps here would create weak points that could fail under load. Here's a detail that would blow your mind. The best carpenters would cut their tenons slightly over size, then use a technique called draw boring to pull the joints tight. They'd drill holes through both the mortise and tenon, but offset the hole in the tenon slightly. When they drove the wooden peg through, it would actually pull the joint tighter than it could ever be assembled by hand. This created joints that got stronger over time as the wood continued to season and shrink. The draw boring process was like performing surgery with an axe. The holes had to be aligned perfectly, and the offset had to be calculated exactly. Too much offset, and you'd split the timber. Too little, and the joint wouldn't tighten properly. Master carpenters could eyeball the correct offset after decades of experience, but apprentices usually needed several attempts before they got it right. But cutting individual joints was just the beginning. Each wall section, or bent, contained multiple posts connected by horizontal beams, and every joint had to fit perfectly with every other joint. The braces, diagonal pieces that kept the frame from racking sideways, added another layer of complexity. These had to be cut at precise angles and fitted with joints at both ends. The braces were particularly tricky because they connected at angles that weren't square. Creating angle joints required a level of geometric understanding that most people today would find challenging even with modern tools and calculators. Medieval carpenters had to visualize these angles and cut them by hand, often working with timbers that were heavy enough to require multiple people just to move them into position for cutting. The dry fit process was the moment of truth. Before any permanent assembly, every joint was test-fitted to make sure everything aligned correctly. This wasn't just checking individual connections. Entire wall sections were assembled flat on the ground to verify that all the pieces worked together as planned. The tension during a dry fit was apparently thick enough to cut with a chisel. When joints didn't fit properly, it meant hours or even days of additional work to correct the problem. Sometimes a joint was too tight and needed careful paring with a chisel to open it up slightly. Other times, a joint was too loose and needed to be shimmed or, in worse cases, completely recut. The master carpenter's reputation rode on every joint, and sloppy work would be remembered long after the house was complete. The preparation of wooden pegs was another crucial detail that separated master craftsmen from amateurs. These weren't just random pieces of wood whittled to size. The pegs were usually made from harder wood than the timbers they would join, often oak or ash, that had been split and shaped to specific dimensions. They had to be strong enough to hold massive timbers together, yet small enough to drive through the drawboard holes without splitting the surrounding wood. Each peg was individually crafted, tapered slightly so it would drive tight, and sized to match the specific hole it would fill. A typical house frame might require 200 or 300 pegs, each one cut and shaped by hand. The peg-making process was often assigned to apprentices as a way to develop their tool skills, but the final fitting and driving was reserved for experienced carpenters who understood exactly how much force to apply. The organizational logistics of this entire preparation phase were staggering. Every timber had to be marked with its position in the frame. Every joint had to be identified and numbered, and everything had to be organized so that assembly could proceed efficiently. They developed marking systems using Roman numerals and traditional carpenter's marks that identified not just which bent each timber belonged to, but exactly where in that bent it was supposed to go. These marking systems were like a code that any trained carpenter could read. A series of notches cut into a timber could tell you whether it was a post or a plate, which wall it belonged to, and exactly how it connected to its neighbors. The marks were cut deep enough to remain visible even after the timber was assembled and the house was complete, creating a permanent record of the construction process. The final preparation step was planning the raising itself. This wasn't something you could do with just the immediate construction crew. Raising a timber frame required the entire community, and coordinating dozens of people with varying levels of experience required the organizational skills of a military commander. The master carpenter had to plan not just the sequence of assembly, but exactly who would be responsible for each task and how the whole process would unfold. Every tool had to be sharpened to perfection, every rope checked for weak spots, and every ladder inspected for loose rungs. Because when you're dealing with timbers that could crush a man if they fell, there was absolutely no room for equipment failure. The master carpenter would create what we'd recognize today as a detailed project plan, except his version was passed down through oral tradition and carved into memory through years of experience. The raising day itself was like medieval community theatre, except instead of entertainment, they were creating shelter that would outlast everyone present. Dawn would break to find the entire village buzzing with anticipation. This wasn't just construction work. It was a celebration, a test of community bonds, and a demonstration of collective skill all rolled into one massive undertaking that would be talked about for years afterward. The first challenge was getting everyone organized without causing chaos. Imagine trying to coordinate 50 or more people, ranging from experienced carpenters to enthusiastic but inexperienced neighbors, all working around timbers heavy enough to require 8 strong men just to lift. The master carpenter had to be part construction foreman, part choreographer, and part diplomat, making sure everyone knew their role without stepping on anyone's pride. The sequence of assembly was critical. You couldn't just start randomly putting pieces together and hope for the best. Each bent had to be raised in a specific order, and the timing had to be perfect. The first bent would go up at one end of the building, carefully braced and held plumb, while the crew moved to the next section. The coordination required was like conducting an orchestra, except every musician weighed several hundred pounds and could seriously injure someone if they got out of rhythm. The actual lifting process was where medieval engineering met pure human determination. Heavy timbers were raised using a combination of ropes, poles, and what they called pike poles, essentially long wooden levers that gave teams of men the mechanical advantage needed to lift massive weights. The technique looked chaotic to outsiders, but every movement was choreographed based on centuries of trial and error. Here's what made it really impressive. They were essentially building a house using nothing but human power and simple machines. No cranes, no hoists, just rope, wood, and muscle. The largest timbers might require 20 or 30 men working in perfect coordination to lift them into position. One person pulling too hard or too little could throw off the entire operation and potentially drop several £100 of oak onto someone's head. The master carpenter would position himself where he could see the entire operation and call out commands that everyone had to follow without question. His voice had to carry over the grunting of men straining against heavy timbers, the creaking of ropes under load, and the general chaos of a major construction project happening entirely by hand. Experience taught him exactly when to call for more pressure, when to ease off, and when to hold everything steady while joints were aligned. The moment when each bent swung from horizontal to vertical was pure drama. All that careful preparation, all those precisely cut joints, all those hours of planning came down to whether the timber frame would stand up straight and true. The first few degrees of lift were the most dangerous. If something was going to go wrong, it usually happened when the bent was at its most unstable angle, heavy enough to gain momentum if it started to fall, but not yet stable enough to support itself. As each bent reached vertical, it had to be immediately braced to prevent it from falling backward or sideways. Teams of men with long poles would steady the structure, while others rushed to install temporary braces. The timing was critical. Too slow, and the bent might topple. Too fast, and someone might get caught under a falling timber. The master carpenter's job was reading the structural stability and knowing exactly when each bent was secure enough to release. But the real magic happened when the wall plates were installed. These horizontal beams ran across the tops of the posts, connecting each bent to its neighbors and creating the rigid structure that would support the roof. Installing wall plates required lifting heavy timbers to the top of the frame and maneuvering them into position while working 12 or 15 feet off the ground on improvised scaffolding. The scaffolding itself was a marvel of medieval ingenuity. Built entirely from wood and rope, it had to be strong enough to support multiple workers, plus the weight of the timbers they were installing. Yet it also had to be flexible enough to be quickly moved as work progressed around the building. The scaffold builders were specialists in their own right, creating platforms that could safely support construction work at heights that would make modern safety inspectors faint. Working at height with heavy timbers tested every aspect of medieval construction skill. The workers had to maintain perfect balance while handling tools and materials, often while standing on narrow wooden planks with nothing but rope railings for protection. Communication became even more critical when workers were spread across different levels of the structure, with some on the ground passing up materials while others worked at the top of the frame. The wall plates had to be positioned with absolute precision. These timbers would determine the final dimensions of the building and provide the foundation for the roof structure. Any errors in placement would be magnified throughout the rest of the construction process. The master carpenter would personally check each plate for level and alignment, making fine adjustments that might require repositioning timbers weighing several hundred pounds. Once the wall plates were in position, the frame would suddenly transform from a collection of separate bent sections into a unified structure. You could actually feel the building gain stability as each connection locked the frame together. The moment when the last wall plate was pinned into place was apparently one of the most satisfying experiences in medieval construction. Years of planning and hours of dangerous work culminating in a structure that would stand for centuries. The pinning process was where all that careful draw-boring work paid off. Each joint was secured with wooden pegs driven through the precisely aligned holes, pulling the timbers tight together as the offset holes forced the joint closed. The sound of pegs being driven home was like applause, a rhythmic hammering that announced each successful connection to the entire community. But the frame was still just a skeleton. The real transformation happened when the roof structure went on top. Installing rafters was like adding ribs to the spine of a massive wooden creature. Each rafter had to be cut to the exact angle that would create the proper roof pitch, and they had to be spaced precisely to support whatever roofing material would eventually cover them. The common rafters were usually cut from smaller timbers than the main frame, but they still required considerable skill to install properly. Each rafter connected to the wall plate at the bottom and met its opposite number at the ridge at the top. Getting the angles right so that all the rafters would line up correctly required geometric calculations that would challenge modern carpenters even with power tools and laser levels. The ridge beam was the crowning achievement of the roof structure. This single timber ran the entire length of the building at the very peak of the roof, and installing it required lifting a long, heavy beam to the highest point of the structure. The logistics were staggering. Imagine trying to get a timber 30 or 40 feet long up to the top of a building using nothing but ropes and human power, then maneuvering it into position while balancing on rafters. The purlin system added another layer of structural support, with horizontal timbers connecting the rafters at intermediate points along the roof slope. These purlins helped distribute the load of the roofing material and prevented the rafters from sagging under weight or wind pressure. Installing purlins required workers to move freely around the roof structure, often working at angles that would challenge a circus acrobat. With the roof structure complete, the frame was finally ready for the elements that would transform it from a wooden skeleton into an actual house. But that transformation would require different skills entirely. The ancient arts of thatching, wall building, and all the countless details that turned a timber frame into a home where families could live, work, and prosper for generations to come. The thatching crew that arrived to cover this magnificent timber skeleton were artists in their own right, wielding tools and techniques that would make modern roofers look like amateurs playing with Lincoln logs. These weren't just guys with ladders throwing straw on top of a house. They were master craftsmen who understood that the difference between a roof that lasted 5 years and one that lasted 50 came down to details most people never even noticed. The material selection process alone would drive modern contractors absolutely crazy. Thatchers couldn't just order their supplies from a catalogue and have them delivered on Tuesday. They had to know exactly which type of straw would work best, where to source it, and how to prepare it for installation. The best thatching straw came from wheat that had been grown specifically for roofing, longer stems, harvested at exactly the right time, and stored in conditions that would preserve its flexibility and water-shedding properties. Here's what made medieval thatchers true masters of their craft. They could look at a bundle of straw and tell you not just whether it was good enough for roofing, but exactly which part of the roof it should go on. The longest, straightest stems were reserved for the ridge, where wind and weather would test every strand. Shorter pieces might work fine for the main roof surface, but put them in the wrong place, and you'd have leaks within the first year. The laying process started at the eaves and worked upward in overlapping courses that created a waterproof barrier through nothing but careful arrangement and centuries of accumulated knowledge. Each course had to overlap the one below it by exactly the right amount. Too little overlap and water would find its way through. Too much, and you'd waste material and add unnecessary weight to the roof structure. The real artistry showed up in how thatchers secured each layer. Using nothing but twisted straw ropes and wooden spars, they created a matrix of ties that held thousands of individual straw stems in place against wind, rain, and the occasional curious bird looking for nesting material. The pattern of these ties wasn't random. It followed traditional designs that distributed stress evenly across the entire roof surface. But here's what would really blow your mind about medieval thatching: the ridge construction. This wasn't just the place where two roof slopes met. It was a complex architectural feature that had to shed water, resist wind uplift, and look good enough to advertise the thatcher's skill to everyone in the village. The ridge was built up in layers, with each course carefully shaped and secured to create a crown that would protect the entire roof system. The tools thatchers used looked deceptively simple, but required years to master. The legget, basically a wooden paddle with grooves cut into it, was used to dress and align the straw into perfectly uniform layers. The technique looked like combing hair, except this hair was covering an entire house and had to stay neat for decades. The eaves knife trimmed the bottom edge of the thatch to create the clean, straight line that marked quality workmanship. Some master thatchers developed signature techniques that other craftsmen tried to copy, but never quite matched. The way they shaped the ridge, the pattern of their securing ties, even the final trim work became their trademark. A good thatcher's work was recognizable from half a mile away, and their reputation could make or break their livelihood. The weather window for thatching was brutally narrow, too wet and the straw wouldn't lay properly, too windy and you'd spend more time chasing materials around the village than actually installing them. Thatchers became expert weather readers, able to predict conditions days in advance and plan their work accordingly. A sudden storm could ruin weeks of work, so timing was everything. From forest floor to finished home, we've watched medieval craftsmen transform raw oak into architectural masterpieces using nothing but hand tools, mathematical precision, and knowledge passed down through generations. These timber frame houses weren't just buildings. They were monuments to human ingenuity, community cooperation, and the kind of long-term thinking that modern construction has forgotten. The next time you see one of these ancient structures still standing strong after centuries, remember the master carpenters who could visualize an entire house in their heads, the communities that came together for raising day, and the countless hours of skilled labor that went into every single joint. Now that's what I call building something to last.